Hello everybody, today I want to introduce you to my paper from last summer, 2022, Bringing Order into 200 Years of Chaos and Gravity. It's about demonstrating that the equivalence principle is wrong and that gravity in fact depends on the material composition of an object. So the gravity per baryon or per quark is constant, but the gravity per kilogram is different. That's because different elements have different amounts of negative binding energy in them. So iron, for example, has a lot, while water has very little, and that's why there's more protons and neutrons in every kilogram of iron than in every kilogram of water. So every one of my papers has this timeline with all the different dates. That's my style of writing papers. And here are the sponsors. Because I'm mentioning a lot of different measured values for the gravitational constant, therefore I omit this part. I omit the units here in this paper. And I'm generally going through all the different measurements of G, of big G, various lists. This list of Gilius, the attracting masses and measurements of G, an overview of physical characteristics and performance, and of this German researcher Ulf Kleinvoss. He has also a very extensive list. Both of them list the material as well. Some of the very old measurements have very low values or very inaccurate values. The first measurement of all is this measurement from 1798, 6.75. This is very anomalous. And this from Poynting, 6.7. The method he used was very inaccurate. He was using a suspended scale in order to measure spring scale. I'm not sure what it is called. Yeah, Michaelis, also not a very good measurement. So the very inaccurate measurements are here given in gray, marked gray. Actually, those are the outliners. Some of them think they have measured with high accuracy, but the strong deviation from the normal value suggests otherwise. Here in this case, from Ponticus, the reason why it's marked gray is because there was some data tampering involved. All these different materials he had measured in 1971, and he got very different values. Each material had a different gravitational constant, and they agreed very well with my theory. But 1 year later, he used computer analysis to basically homogenize the data. This is also sometimes done in climate research. It's a form of data tampering because people get very unhappy when their experiment doesn't confirm the equivalence principle. This was also the case with Hale. Yeah, he measured different materials, and he got different gravitational constants for the different materials, and he was very unhappy about it. He noted it in the 30s. He wrote a paper and noted that the deviations between different measurements of the same material are very small, but between different materials they're very large. So he was very unhappy about it, and so he continued his work and he tried to reach higher precision so that the problem might go away. He saw it as a problem, not as a discovery. So he did that for another 12 years until 42 and published another paper. But again, the anomaly remained and nobody seems to care about this. And the purple entries here, they are low accuracy. Okay, here in another list it was 0.04. So generally, if the accuracy is if the deviations are larger than 0.01, then I mark them purple. And so in the analysis, this is important. So we can look at the average when including the purple and when not including the purple ones. Yeah, stainless steel is generally, there are many different types of stainless steel, but the differences are very small. So it's not worth distinguishing. Also, it's hard to know which type of stainless steel it was exactly. Basically what happened in the last 20 years is that this physicist from China, from Guangzhou, his name is Luo Jun. Yeah, in English it's Jun Luo. He measured stainless steel, the gravitational constant of stainless steel, with very high precision, and this is why his value is taken to be the standard now. Like the average between these two is 6.67430. But it's really only based on stainless steel, and they chose stainless steel because it reached the kind of value they wanted, and they didn't want to switch to other materials because they got different values. They didn't like that. And here more and more values. I have all in all 91 different measurements, and these are the original values measured by Ponticus. He's from France. He published that only in French. I contacted him. He didn't quite remember much about this. I think he went into climate research later, so he really forgot everything about this, or most of it. Although his measurements are quite precise. So here my theory, SPD, space particle dualism, is the name of my theory. It predicts a value of 6.668 for lead, and we find the measurement is 6.668. Then brass, 6.674, measurement is 6.674. Again here copper, SPD predicts 6.674. The measured value is 6.674. Mercury, 6.668, and the measured value is 6.666. Only silver has an unsatisfying result. Agreement within margins of error here for all of them, yes, except for silver. And unfortunately, that's the only silver measurement I'm aware of. His measurement was quite extraordinary. He's the only one who measured the gravitational constant of lead with an accuracy of 4 digits. The only one of 2 who measured brass accurately to 4 digits. The other one is Kleinvos. One of 3 to measure the gravitation of copper accurate to 4 digits. Yeah. So also mercury, the only one to measure mercury accurate to 4 digits. Okay, yeah, that's what I already explained. he published another paper, and just all the values became pretty much the same then. And Taylor noted this in his paper, where he analyzed various measurements, and he said, since the three measurements are not consistent, at least one of them contains an unidentified systematic error. And the uncertainties are the statistical standard deviation of the means of each series of 10 measurements. Unfortunately, insufficient information is given in Pontic's result to properly evaluate his systematic error. Indeed, he obtained a significantly different result from measurements taken in September 1971. So he basically, he also debore. Unfortunately, the documentation of the result is obscure and incomplete. The author announced a final detailed report, which, however, to my knowledge, was not published. Yeah. And the measurements are evaluated using a computer. It's basically data homogenization, which made all the different values become the same, or more or less the same. Okay, this is pretty long. Here I'm talking about Eötvös. He made freefall experiments where every material actually had a different freefall time. But because the differences were very small, and Eötvös was very eager to prove the equivalence principle to be correct, so he just hid it in the error bars. If the error bars are large enough, then you can ignore the differences. But later, Fischbach discovered those differences in the original work of Eötvös. And that started 10 years of intense experimental research. But because Fischbach said that Fischbach, instead of saying that this means gravity comes from the strong force, is a side effect of the strong force, he instead said that that there's a fifth force correlated to the strong force, and it has a reach of 20 meters, which is totally arbitrary. He basically just didn't want to give up Einstein's equivalence principle. And so everyone who tried to test Fischbach's idea, instead of testing this material dependency, he showed that it has to do with how many protons and neutrons you have, how much inertia mass versus gravitational mass. His equation was basically the same as my initial equation, just not as precise, because later I made a more precise formulation of it. Karagios, he's a Russian physicist. His work was not very good, but I don't want to get into all the details. There are many different people who have made measurements. So these are some long-range measurements which are very inaccurate. It seems that these measurements are very difficult to do at very large scales. So the way we calculate this is we have the gravitational constant of hydrogen, which I derive in another chapter, but the derivation is it's basically obtained from the gravitational constant of iron or stainless steel, which it's like the inverse of this one. So here we have number of protons and mass of protons, number of neutrons and mass of neutrons. So here, because it's for one material, so here's the average. This mu is for average. So this is the gravitational mass, and this is the mass of the element X, like any element. This is the gravitational constant of the element X. So, and this is the gravitational constant of hydrogen, 6.6136, and for obtaining this basically we calculate the same as here, but the numerator and the denominator just switch places. And here we would have gravitational constant of iron or stainless steel. Actually, when I calculated this, my most precise calculation was distinguishing between stainless steel and iron. There's a tiny difference, but I want to be precise. So here basically we look at we have inertial mass and gravitational mass, and gravitational mass is basically just these here these are the percentages of the different ingredients here, and here we have the number of protons, and here's the number of neutrons, and this is the atomic mass of protons and neutrons, and here's the percentage. So and then here are the predictions. Platinum, so here SPD agreement within margins. Here SPD agrees in most cases, while GR doesn't agree. No, so it means general relativity fails in all these cases. It's failing. So the only cases where SPD fails is here with copper, but then when we go to copper according to Newman, then it's agrees again. Where else? Okay, here with glass. Okay, glass is a problem, but it was only measured by Hale and nobody else, and this is also Hale. So this is from the 1920s. Yeah, and silver, Ponticus is just a single measurement, and platinum also Hale in 1926. So yeah, pretty good agreement for my theory. Comparative analysis. This is looking at if they all line up in a hierarchy to see which elements violate the hierarchy. The gray ones violate the hierarchy. Those are the bad measurements, like gold, glass, uranium, silver. They are not very precise measurements. And here I calculate the chance against odds that this is all a coincidence. Yeah, here again. The chance that I'm wrong is basically 1 in 10 to the power of 18. Here I talk a bit more about historic stuff. Brush also made some free fall experiments, which were completely comparative. He was just comparing which is faster, which is slower. He had some mechanism in the floor where when you drop something on the floor, then a switch is turned, and then it's pushed, and then basically you can know which one was first. He also did Cavendish experiments and an oil drop experiment. Very few people know about this. Basically, the oil drops, they attracted each other when they shouldn't, because he was using the same density for both the liquid and the oil drops. Like the oil, obviously he cannot adjust the density of the oil drops, but he basically made the liquid to have exactly the same density as the oil drops. So basing gravity only on mass, simply on mass, cannot explain his oil drop experiment. They shouldn't have attracted each other. Yeah, so that's my paper from last summer. It's one of my most important papers. And also my paper with the most references here, 91. Okay, that's all for now. I hope you enjoyed the video and see you soon.